All right, welcome back to another episode of Science with Surbeck. Today we're talking about section 6.2, which deals with the classification of the elements. Our objectives for this lesson is to explain why elements in the same group have similar properties, and our other objective is to identify the four blocks of the periodic table based on electron configuration. Okay, so we start out here with valence electrons, which we already introduced in the last chapter, but valence electrons are the electrons in that outermost energy level, or we see here the highest principal energy level. And so to help explain that here, I have this chart, and it shows here our element hydrogen. Its valence electrons are found in period 1, or the first energy level. And if you go all the way down here to potassium, our valence electrons for potassium, which are in the same group, are found in period 4. So even though something has the same number of valence electrons, it doesn't necessarily mean those valence electrons are in the same spot. As we go down the periodic table, they're going to increase in the energy level, and they are going to increase in the energy level of the valence electrons. So just a reminder here, I just grabbed a periodic table. Our valence electrons, we can easily find that by going group by group. Remember, this first group here had one valence electron, and just a reminder, valence electron I abbreviate as VE, and we go to that second group, which gets two valence electrons. Now we skip over the transition and intertransition metals, get to the group with boron. That group had 3 valence electrons. Carbon's group had 4 valence electrons. Nitrogen's group had 5 valence electrons. Oxygen's group 6. The halogens had 7. And then our noble gases had 8 valence electrons. Okay? Now, again, just to emphasize this, elements in the same group have the same amount of valence electrons. However, where their valence electron is increases or expands to a higher and higher energy level. All right, so let's talk about this again in just some specific detail here. So valence electrons and the period. Just to reiterate what I've said a couple times here, the energy level is equivalent to the period in terms of the valence electrons. So our example here is lithium. All right. So lithium, it is found in period 2. So that would mean its valence electrons are in the second energy level. Okay. Again, found in period 2, valence electrons are in the second energy level. Gallium, which is found in the group with boron, has 3 valence electrons, and those 3 valence electrons are found in the 4th energy level because gallium is in that 4th period. Okay? So again, the period number is equivalent to that highest energy level. Something to keep in mind as we go through and we keep identifying the importance of our valence electrons. All right, so now we get to things that we have discussed previously, and I just put it in some word representation here. So with our groups, we can correspond that to specific valence electrons. The big what if, or the big adjustment we have to make, is for those transition metals. So transition elements have 2 valence electrons, okay? And that's because if we think back to the electron configuration periodic table, our transition elements here start with the group with scandium, go all the way over to the group with zinc, and down here at the inner transition metals. The highest principal energy level is equal to that period level. And remember, we went down one number, so we went 4s and then 3d for that d level. And that's why there is always 2 valence electrons. Now later on you'll learn there are some exceptions with those transition metals, but here in this class we're going to consider those transition metals to have 2 valence electrons. Okay, so we've discussed that. It's on the periodic table, but just to reiterate that, or just to emphasize that again, that all of these transition metals would have 2 valence electrons, and that would stop right here with zinc, and that also includes our inner transition metals. Now again, in some advanced classes there are some exceptions to this, but we're going to keep it simple here and say inner transition metals have 2 valence electrons. All right, so now what we're going to do here, we're going to bring back what we talked about with valence electrons, and we're going to talk about our sublevels. So it's really important that we emphasize some of the sublevels and their importance to, or the role it plays in valence electrons. Okay, we've already talked about this in some depth with chapter 5 when we introduced electron configuration, but the main takeaway here is this. There are 4 blocks or 4 sections of the periodic table, and what they do here is this. We divide it into S, P, D, and F sublevels, and we have to remember, as we go down the periodic table, as the period number increases, the highest principal energy level increases, and so we have to keep that in mind. Now, we can talk about this, what different subblocks each period contains, but we're going to go through this in more detail. All right, so now we move here to S block elements. Remember, the S block here is shown on this periodic table as our yellow elements, and they consist of group 1 and 2. Now, an S sublevel only has 1 orbital, and remember, each orbital can only hold 2 electrons. So that S sublevel, because it only has 1 orbital, can only hold a max of 2 electrons. To show this on the periodic table, again, group 1 and group 2, that is our S block. Okay, now we scroll over to our P block. So our P block elements, they're shown here on this periodic table in purple, and the P block elements are from groups 13 all the way to 18 on the periodic table. And these P blocks elements are very important because their valence electrons occupy the S and P orbitals. Now this is going to play a role here when we talk about noble gas, but each P sublevel has 3 different orbitals. Each orbital can hold 2 electrons, so if we take 3 times 2, a P sublevel can hold a maximum of 6 electrons. Now, the importance here about noble gases, I said we would circle back to valence electrons in P block elements going through or occupying the S and P orbitals. The importance to this becomes the octet rule, which we'll talk more and more as we go through this class. But in our P block elements, we have the noble gases, and noble gases have a full set of 8 electrons in their outermost S and P orbital. That's really important as we go through and as we start to talk about chemical bonding and why elements and atoms bond together. All right, so let's go on and keep talking about our final 2 blocks of the periodic table. So our D block elements is our transition metals, and here this is shown in blue, and they consist of groups 3 through 12, and they are going to just fill those S orbitals. Remember, I'm going to pull the periodic table back. Remember, all of these had 2 valence electrons, because if we take, for example, scandium, we went 4s2 and then 3d1 with our electron configuration. So the valence electrons are only filling that s level. And that's why they have their valence electrons occupying those s orbitals. That's a really important thing there. If you want to highlight that point, it is essential. It is crucial. Now, D sublevel has 5 different orbitals. Each orbital can hold a max of 2 electrons. So 5 times 2 is 10. The D sublevel can hold a max of 10 electrons. This business here on point 4, D sublevel fills prior energy level. So remember, here with scandium, we went 4s2 and then we went backwards to 3d1. Okay, so that's important. We'll talk about that again with the F block elements. All right, so last thing here that we have to talk about is our F block elements. Remember, these are just called the inner transition metals. In this periodic table, they are shown here in green, and they're usually detached and placed at the bottom of the periodic table. Now again, their valence electrons only fill the s orbital. And I know we may have to imagine this, or we have to think about our electron configuration periodic table. But if we got here at period 6 and we went through cesium and barium, we would say, hey, the electron configuration for barium would be that 6s2. And then we get down to the lanthanum, cerium, and so on. This would be the 4f level. Okay, so these would be the 4f level. The highest principal energy is 6. All right, so again, we get to this point here. There are 7 orbitals, 7 different orbitals, so 7 orbitals in our F block. Each orbital can hold a max of 2 electrons, so 7 times 2 is 14 electrons. The whole sublevel can hold a max of 14 electrons. Okay, so now we have this. The F sublevel, remember, when we talk about electron configuration, I'm going to emphasize this. Talking about period 6, we went 6s2, and then down here at the inner transition metals, we went back to the 4f. That 4 is important because it goes back 2 energy levels. So that's what we have to think in or keep in mind when we account for the valence electrons, and we'll get some practice with that. All right, so I hope you have enjoyed this particular episode of Science with Surback, and if you haven't done so already, make sure you subscribe.